Hi. I really like the way that throughout that talk Dan kind of implied that I had more of an idea of him about what was happening or how Java worked, but in fact we both learned the same amount on that day, so it was good for both of us. Right, I'm Mark, I work for Elmax as well. This talk I kind of wrote after we spent the best part of 6 months tuning our Linux systems for low latency. And so I just kind of want to share some of the techniques and tools that we used. It's quite representative of our architecture and the systems we work with, so your mileage may vary given on whether it's helpful for you or not, but hopefully it will be of some use. So before I start, I should qualify that it's the Linux operating system I'm going to talk about. The kind of primitives involved will be similar for other operating systems, but the tools and names of commands are Linux specific. So it's obviously more use if you're running on Linux, not Windows. Right, so first off, it's not the operating system's fault. I should point out, Linux is a really good general purpose operating system. It targets many different platforms. And for us, being a low latency exchange, it's quite a special use case. So we're not using the operating system in its kind of out-of-the-box configuration. So we need to provide some hints to the operating system to kind of tell it how we want it to behave in order to get the results that we want. So the reasons why you would care about this. It doesn't apply to all scenarios, but some useful places where it does. The low latency applications, as I've said. And by low latency, I mean where your response times are generally under a millisecond. So I mean, it's quite an aggressive target, but you'll really start to notice these kind of techniques come into their own when you're down to those sort of numbers. If you have compute-intensive workloads, where you kind of need to make sure that you're getting as much CPU time as possible, or if you have really long-running jobs where they sort of run for days and shaving 1% off saves you a significant amount of CPU time and expense. So it's not for everyone, but if you have any of these kind of use cases, it could be useful. I'm going to just define jitter quickly. So if you look up on the interwebs, you'll read that it's a slight irregular movement, variation, or unsteadiness, especially in a signal or electronic device. But when we're talking about jitter, especially in low latency systems, we're talking about variation in response time latency. And this tends to manifest itself as long tail in response time. So your average response time might be very, very good, but 1% of the time or 0.1% of the time, you'll have kind of latency outliers, and that can be a bad experience for your customers. So when we talk about jitter, we mean the kind of worst case latency that your customers can expect to see. And obviously we want to minimize that so that everyone gets a nice fast execution. So how can we deal with jitter? To start with, we want to deal with the low-hanging fruit. So this is pretty obvious, there's garbage collection. So it tends to be the bane of most Java applications. So you either have to go garbage-free, get your programming techniques changed so that you're doing lots of object reuse and pooling, or deploy the Zing hammer, which is what we do at Elmax, which kind of makes those problems go away, so you can concentrate on other stuff. If you have any slow I/O on your application's fast path, you obviously need to take care of that with caches or what have you. And then once our response times are under about 10 milliseconds, then that's the kind of threshold where we can start looking at these kind of techniques. And obviously it sounds stupid, but you need to make sure your code is running. And we'll see some tools to help us figure out whether that's happening or not. But before we start any kind of optimization procedure, the most important thing is to be able to measure it first. So there's no point in trying to make changes to your system if you can't tell whether the changes you're making are having the right effect. So we need to validate that any changes we make are good. Typically, the best way of doing this is through end-to-end testing, which is repeatable and continuous. So we should treat performance testing as part of the continuous delivery pipeline to make sure that we're always kind of running the same tests against our systems, and then we can start to change one thing at a time. We need to make sure we're using realistic loads. So we spent a long time at Elmax modeling and analyzing the kind of traffic patterns that we see in our production environments, because we need to make sure that we're exercising our systems in the same way that our customers are, and to be able to make sure that we can kind of ramp up that load by 2 times, 3 times, 10 times to make sure that we can meet our capacity targets, and to see where our system breaks, because all systems do break, so you want to know how it's going to break and what the warning signs are, so you can kind of get ahead of it. Part of this technique, I think I said, we want to change one thing at a time and observe. So piling in a whole bunch of changes that you've read on Stack Overflow are the best things for low latency, and just flipping flags is probably not the most measured and scientific approach. And it's very difficult to figure out what was the one thing that did make an improvement if you do make a load of changes and you see some kind of benefit. Right, so I'm going to go on a quick refresher, which just so everyone's kind of on the same page. This is a diagram I scribbled describing what the kind of hardware layout you'll see in a modern server system. So the kind of servers that are deployed in the Amazon cloud, or if you have your own hosting, probably if you've got modern servers from the last couple of years, they'll look something like this conceptually. At the bottom we have the chassis, which is the physical chunk of metal that you plug into your rack. Sitting in the chassis, we'll have one or more CPU sockets into which gets plugged a physical processor. And there'll be a PCI bus attached to each of those sockets through which your network interfaces will be connected. Each of those sockets will have a chunk of DRAM, and that's typically in the 64, 128 gig, something like that. And the processor itself will have an L3 cache, which is largest. There's a QPI interconnect between the two chunks of memory. And then further up, the processor these days will have a number of physical cores on them. The core is the kind of the physical part of a processing unit. That will have an L1 and L2 cache, which are getting progressively smaller and faster as you move up the stack. And then the hyperthreads are like a logical processing unit. So there's a little bit of duplicated hardware which allows the hardware to present what looks like two actual CPUs which are actually running on the same physical core. As I sort of talk through examples of how we can utilize these resources, that's kind of what we're talking about, just to set some terms. So our operating systems are multitasking, so Linux is a multitasking OS. And when we're using computers, your laptop or your phone or large wide server systems, generally you've got more tasks that can become runnable than the number of hyperthreads on the machine. And the OS must share out those hardware resources between all the things that want to grab some CPU time. So if you've got a very kind of parallelizable workload, more software threads than you have logical CPUs, and they're all trying to grab CPU time, there's going to be contention there. So the operating system has to make some decision about how it will share out those resources, and it could be clever, dumb, fast, or slow. Ideally, we'd probably want it to be clever and fast, but I think that's probably quite difficult because it would assume some prior knowledge about your workload. So what Linux tries to do is be fair. The default scheduler, which you'll be using in Linux, is the CFS, which stands for the Completely Fair Scheduler. So its kind of overriding concern is to make sure that everything gets the CPU time it needs. And its operation is based on having a queue per hyperthread or logical CPU. So queue is quoted because I think it's a balanced tree of some sort, but it's an ordered data structure. And it needs to be ordered for fast usage because the way the scheduler works is when an executing task calls schedule to say, okay, I've used up my CPU time, or it gets scheduled off because it's exceeded its quota, the scheduler will choose the task within that data structure with the lowest runtime so far. So if you're a process which wants to become runnable has been getting starved of resources, it is more likely to be at the head of the queue. And in this way, the fairness comes in, and the scheduler is trying to make sure that everyone gets a little bit of CPU time. So after the task is executed, the runtime is updated for that particular task, and it goes back into the data structure. There's a hint to the scheduler, so we can set the priority of threads with nice and other such tools. And this used to, back before the CFS, this actually used to mean that they would kind of, those processes would go ahead of the queue, but now it just kind of hints to the scheduler that there should be a bit more execution time for this particular task if it's given a higher priority. And all the tasks within the system are load balanced across the hyperthreads. So if you have a busy CPU and the scheduler notices that there's a task that has become runnable within that CPU's run queue, it's free to balance that across to another hyperthreads queue in order to get some CPU time. So it's fair within a queue, and it's also fair across the system, so everything gets to run when it needs to if there's enough resources. I'm going to talk about an example application. If anyone's seen my colleague Sam's talk on the LMAX architecture, this is a slightly skewed diagram that you might have seen before. A lot of our services are kind of based on the disruptor, using the disruptor as a queue. So we'll typically have a data source, which might be a file system or a network card. We'll have a queue, which is usually a disruptor instance, almost exclusively. And we will have a number of threads reading from the tail of that queue. And in the diagrams that I'm going to show, the green arrows represent threads. So these are software Java threads in our world. So here we have a data source where there's a thread reading off a network card, so let's say dropping messages onto a queue. And we have a thread which is reading it off to do logic, and another thread which is reading it off in parallel to do some journaling to disk. And what we want to do is make sure that the thread which is servicing the network card can always get CPU time to read from the kernel's buffers, and that the thread which is doing the logic, let's say that this is latency sensitive calculation, that it can get CPU time when a new message comes into the queue, and that the journaler can journal to disk in a timely manner. So this is a nice simple architecture. We can take a 48-way Dell box and happily run our 3 threads on it, and there will be no contention whatsoever. But reality is slightly different. So our lovely 3-thread application runs within a managed runtime, which in this case is the JVM. Same would apply for .NET runtime or anything like that. And we have other threads within that runtime. So we have garbage collection threads, any libraries you're using, mobile spin-up threads. You can have all sorts. I mean, if you would just run JStack on a running process, especially a web server, you'll see how many hundreds of threads there are. And while most of those threads aren't working all the time, they will occasionally want to wake up and do work. And if they happen to contend with your threads which you really want to be low latency, then you could run into problems. And it gets worse. There's not just your managed runtime. There's also the operating system. And the operating system also has a whole bunch of threads which it's trying to schedule in order to do work. And we've come across numerous problems where we've had noisy OS processes which have kicked our application threads off, just from handling paging requests and things like that, which has taken some time to track down. So although it won't happen all the time, there's always the chance that your runtime or the operating system is going to contend for CPU resource when you really want it. Okay, so given this rough layout of one data source reader and a couple of other threads which are processing a queue, what we really want to do in order for low latency transmission between threads is to optimize for locality. So we would ideally like to run all our business threads or our important threads on the same physical node, because that means they're going to be able to share the L3 or the DRAM, so we won't pay the QPI cost of going to hitting the other bank of memory. And we want to make sure that they can possibly share the L1 and L2 cache, well, the L2 cache, when they're transmitting this data. So given that, we are going to try and deploy our application in the following configuration. So we've got our 3 important threads. We're going to put our data source reader onto logical CPU 1, our logic thread onto CPU 3, and our journaler thread onto CPU 5. Importantly, we are going to ensure that nothing runs on the sibling logical CPU for those target CPUs. And we do this because the way Intel hyperthreading works, if the CPU can detect, the physical core can detect that there's no task running on one of the logical CPUs, it will kind of shut down or idle that particular logical CPU, and you'll end up getting the full capacity of the physical core for your executing thread. If you have things that are contending, then the instructions which are being generated by the processors on logical CPUs 0 and 1 would end up being interleaved. And if you kind of get worst case, then you end up seeing half the clock rate of your physical core on each of the two logical cores. So we found that for best throughput and best latency, try and make sure that you've isolated the other logical CPU on your physical core. That's how you get the best benefit. So that's our target. How do we start to do this? Start with the metal. So first of all, we need to tune the BIOS. Luckily, I'm not going to go through tuning the BIOS. There's a whole other talk on that, which I don't have, and which would be really, really dull. First off, read your vendor's BIOS settings. Make sure that you've got the low latency switch switched on, because there really is, in some, especially in Dell BIOSes, there's a low latency on-off, which is awesome, so switch it to on. There's a bunch of other things to go and check out to make sure that you're getting the right behavior from your system. But anyway, so you need to take care of that first, otherwise it will introduce noise, which is going to cause us to have difficulty in measuring certain signals later on. So once we've figured out, sorted out the physical side of things, we want to know what's available on our hardware and what we have to play with. So we use something called LSTopo, which is provided by HWLock. So if you're running Linux, go and install HWLock and have a look. It will show you the hyperthreads on your system, the physical cores, NUMA nodes, and the PCI locality of any devices which are plugged into the bus, so your network cards or what have you, or block devices. And it looks something like this, which hasn't rendered too badly. Just to give you an idea of some detail, this is the one socket of one of the old generation servers that we used at LMAX. What we can see here is that LSTopo is showing us the hyperthread, the physical core, the banks of caches available to each of those physical cores. So we can kind of see that L3 starts off as 15 meg, L2 is 256K, and then L1 is 32-bit for instruction and data. And we have a NUMA local RAM of 32 gig on this particular system. It's upside down compared to my other diagram, just to keep everyone on their toes. So now we know what we've got, right? We want to, we already know that we want to kind of schedule a task here, a task here, and a task here, and make sure that there's nothing running on these threads, and we want them all to be on the same same NUMA node, and we want to make sure there's nothing else running on those. So our approach is to reserve and use specific resources. So the first step is to use the isol CPU's command line parameter, and this basically says to the scheduler that it can't schedule tasks on certain CPUs. So if we add isol CPUs equals 0 to 5 and 10 to 13, that will tell the scheduler that it can't put any kind of userland processes on there. And you normally add this in your grub conf or something like that, and then next time you restart your system, you can go and have a look in proc shed debug or something, and you'll see that there are no userland tasks being stomped all over those CPUs. We can use the task set command to restrict our runtime to run on a certain set of CPUs. And task set is just a standard tool that's in all the Linux distros. So we would say task set -c 10 to 13, and this will say it will launch the Java command, and it will tell the scheduler that the Java command and any child processes that it spawns will be restricted onto running onto CPUs 10 and 13, and they'll be effectively load balanced off. And then from within our application, we've got 3 hot threads that we want to set onto certain CPU cores, CPU numbers. We can use the shed set affinity command. So this is in libc, but there are a number of Java libraries which you can use to call that from Java using JNI or JNA or what have you. So if we deploy those three wonderful techniques, we end up with something like this. Shed set affinity does the job of putting our three important threads onto those three logical CPUs. And we know that we've used isol CPUs to tell the OS that it can't schedule stuff on the sibling hyperthreads. This bit is everything that's not in isol CPUs, so all the operating system threads will get stuck onto those CPUs. Happy days. And we're using task set to restrict all the managed runtime threads onto another set of CPUs, which again is not going to contend with the operating system threads and is not going to contend with our application threads. So that looks really good. This is what we initially worked with, and it doesn't work because you've told the operating system scheduler that it's not allowed to load balance across CPUs 10 to 13. So what happens is you launch your Java process using task set, and the Java process and all the GC threads and all the application threads and everything else that's not managed with shed set affinity ends up getting scheduled onto CPU 10, and it can't go anywhere else. And the first time you get a parallel new collection, all the GC threads get scheduled onto one CPU and the whole thing falls over. So that's first failed attempt. Don't try this at work or at home. So one solution, and this is the solution we ended up working with, is to use something called CPU sets. CPU sets allow you to create hierarchical sets of reserved resources. In terms of CPU and memory, there are userland tools. So because it's Linux, everything is actually controlled by echoing things into various file systems. But there are some, or there is one set of nice userland tools to do it. It's only in the SUSE distribution, so if you want to use it on anything else, you kind of have to build it yourself. But it's not too hard to do. It looks something like this. What we're going to do is call cset, set, which says, I would like to create a set, and we give it a name called system, or /system, because it's a file system, so it has to have a path. And we say we're going to have CPUs 6 to 9 in that system CPU set. So that's where we want all the operating system threads to run. Then we can call cset proc, so processes. We pass it the move command. And we say, I want you to move from the root set. So the when CPU sets is initialized, / is root, so it's where all the operating systems processes start off, and we want to move them into the system CPU set. We would like to move unbound kernel threads, so there's a bunch of housekeeping threads that the kernel starts up per CPU, which you don't necessarily need to be there. -- thread says move the child threads, and force does what it says. It hasn't caused anything to crash, probably doing a good thing, so I left -- force in there. Hopefully I'm describing the right thing. And that looks something like this conceptually. We start with CPUs 0 to 13 on this mythical 14 CPU box, and we move all the threads that were in the root CPU system, CPU set into system. So this is essentially shifting all the OS workload off to somewhere else where it's not going to interfere. That's one part of it. Now we need to sort out our application. So here we create another CPU set. This time calling it /app. Then we use cset proc again. And this time we say we want to execute something into the CPU set /app. And then we use task set to restrict the managed runtime threads within that app CPU set. And once again, we're using shed set affinity in order to set the affinity of our low latency threads. And this looks something like this. So what we end up with is all our OS threads on CPU 6 to 9. We have this two separate chunks of CPUs in /app, and we've used task set to restrict the runtime to 10 to 13, leaving 0 to 5.3. So back to our diagram, our deployment. We're now running in /app. And we're using shed set affinity in order to restrict those threads to those CPUs. Everything else in the operating system is running /system, and we have all the managed runtime threads are running in /app. And we get around the problem with the load balancing threads here because the way CPU sets work, the CPU set is just a different scheduling domain. So the scheduler is free to work within /app. So it will load balance things across all the CPUs that are in app. But because we've used task set, we've restricted the JVM threads just to be on those few, and we're using shed set affinity for the other ones. So that worked pretty well. It did improve our latency quite a lot, but of course it was only the start of a long and eventful journey. So how can we find out whether we're at our goal of making sure that our application threads are actually running? If you remember several slides ago, we said we want to make sure our program is doing stuff. I learned quite a lot during this whole exercise about Linux tracing tools, so I'm going to just kind of briefly introduce a couple. The first one I'm going to talk about is perf events. If anyone's been reading Brendan Gregg's blogs over the last 2, 3, 4 years, you'll have read something about this already. It's well worth checking out if you haven't. Perf events is a sampling tracer. So it works by looking at various trace points within the kernel, and when a counter overflows, it will take a sample of some data. It has static and dynamic trace points. So the static trace points are compiled into the kernel source code. You look for methods called trace underscore, and you'll generally find all sorts of library code calling out to the trace methods. There's also the possibility to do dynamic tracing, so you can use perf to probe user libraries and see what methods you can kind of hook into to get various other stats out of those. It's got a very low overhead because it's just sampling, so it basically works by enabling a flag somewhere, and then when the counter trips over very, very infrequently in terms of CPU time, then a sample is recorded to an in-memory buffer. And this is a really good starting point for digging deeper. So if you want to see what's happening on your CPUs, start with this. You won't perturb the system too much, and it will give you a lot of pointers about where to go next. And we can use perf list as root to view the available trace points that we have within the system. So again, if you're running Linux, if you haven't got perf installed, yum install or your equivalent and have a look. And the trace points that are available just within the kernel, there's a ton of them, but they're sort of broken up by category, so network, file system, scheduler, that kind of thing. And we're going to have a look at one of the some of the scheduler events. So we can ask our CPU what's happening in a very nice way. This command will tell the perf subsystem to record scheduler switch events on CPU 3. So when the shed switch event is emitted whenever the scheduler moves one task off the CPU and puts another one in its place. So yes, sample task switches on CPU 3. We can run perf report, which is the kind of side command to it, and this is quite good if you've got a recording with lots of different events in it. It will kind of give you histogram breakdowns and that kind of thing. It's good for drilling down into. If you want the raw data, perf script is your friend, and this will basically give you a textual representation of the events that have been captured. And it's best if you've got just kind of one single event that you've been tracing, if you're looking at something in particular. So we can see an example of said output. So here, this is shed switch events on CPU 3. So on CPU 3, we had cleared off the OS threads, used task set to make sure our application threads weren't going on it, and we'd use shed set affinity to make sure that only our Java thread was executing on CPU 3. And lo and behold, we have something else getting in the way. So we can see the Java command, that's our program that's executing. There's the PID. This is the timestamp to microsecond resolution when this event was emitted. That's the event name. So these all kind of follow a common format, about up to this point. And then this is the payload of the trace data at this point. So this is telling us that the Java PID with priority 110 was runnable, so that's the R, and it was switched out in favor of K-worker thread, which has a higher priority note, 120. And then a bit later on, we can see that the K-worker thread was switched off again in favor of the Java thread coming back in, and the reason the K-worker thread was switched out was because it was in the sleeping state, so that's the S there. So we've got kind of a smoking gun, right? There's, we can see that something else is getting on our CPU, and we've said that we really want the CPU all to ourselves, and we've jumped through some hoops so far. So at this point, we kind of need to figure out why is the K-worker thread being scheduled onto our CPU, and is there anything we can do about it? So at this point, I can introduce another tracing tool called ftrace, which stands for function tracer. So this tool has the same capabilities as perf, so it's got static and dynamic trace points. It can also kind of trace functions in the code, which we'll get to in a bit. It's got higher overhead because it's not working on sampling counters and just taking an event every so often. It's instrumenting your code and capturing everything. It will capture everything. It can provide you with nice function graphs, which are really useful for seeing what the executing code is doing, because once you can see the function names, you can go and trace it back up into the kernel source, and therein lies the answer to all your problems if you can just find it. There's a nice front end for it called trace command. So this is the other install this if you want to play around with this kind of thing. Trace command lets you do recording, reporting, and that kind of thing. It's the equivalent of the perf record. So an example. What's our kernel thread doing? Using the trace command executable, we can say we want to record PID P PID, and we would like to use the plugin function graph. So ftrace comes with a bunch of different plugins. There's stuff for IRQ, wake-ups, and many other things. Function graph is the one we're going to look at here because it's a really good way of finding out what the hell programs are doing executing at the moment. So this will trace all the functions that are called by this PID, and then we use trace command report, which will take the recorded data. So when ftrace is running, it's copying as a command is executing on CPU and calling out to ftrace, that data is being stored to a per CPU ring buffer, and when you run trace command report, it goes and collates all that binary data and munges it into some readable text for humans. So this will display for us the captured trace data, which looks something like this. This looked really good in 16 to 9. Right, so just quickly go through it. This is all the same thread, so what I've done specifically is say I only want to trace what the K-worker thread is doing. And the function graph plugin will give you microsecond resolution timestamps, same as perf. And it will tell you when you're entering a method. So that's function graph entry, that's I'm entering this method, then I'm entering this method, then I'm doing some other stuff, and I've elided some here. But it gives you the whole kind of call trace, which is really awesome if you like that kind of thing. And it's a bit like stepping through with the debugger, but after the fact. The thing which is kind of interesting here is that it tells you the total time taken between blocks of code. So the function that's entered into right up the top here is called process one work. And if you line up the braces way down the bottom here is where the kernel worker thread returned from process one work, whatever that mysterious thing was. And it took 86 microseconds. So again, depending on your kind of application, 80 microseconds might be trivial and not something that you're worried about. But if we're trying to get our end-to-end response times through our system in a couple of network hops of 100 microseconds, then this is really going to cause us an outlier. So that's 80 microseconds when our program wasn't executing. It couldn't do useful work because it had been bumped off by the kernel in order to do some other work. And there's other considerations here. So it's not just the time that it was off CPU, but the kernel worker thread, depending on what its workload was, it could have polluted the L1 and L2 cache and caused some sort of thrashing there so that when our Java program came back on, it then had a cold cache which it had to service cache hits in order to get back up to full speed. Some of that is the overhead of tracing. So if you were to just run monitor just the switch events, you'd be unlikely to see something that took that long for this workload, but it gives us an idea of the kind of times that our threads can be off CPU due to something else. So that's one example, the delightful cache reap function. So during the course of the tuning we did, this was a 3.18 kernel, I think. There are a number of things that I stuck in here that were just kind of interesting that saved, that it took us a long time to figure out and might save some time for someone else. So cache reap was the function that was being called in that kernel thread. And that's a function used by the slab allocator, which was the Linux kernel memory allocator. In previous versions, recently that was changed to the slub allocator, which doesn't suffer from this problem. We found during our testing, though, that our overall latency was better with slab, so we stuck with it, but it does mean that we have this, this cache reap function that gets called every so often and kicks our threads off. VMstat update. So if you've ever run VMstat on your machine and seen all the lovely stats come out about CPU time and what programs are taking time, this is generally called or called by the kernel once per second on every CPU within your system. So if you're interested in getting the stats from your system, you're paying a cost in terms of CPU scheduling, because there are a number of jobs which are just executed on every CPU all the time by the kernel. This also has been removed in more recent kernels when you only have one process running on a CPU. Because if you've only got one thing executing, then there's no point in kind of updating runtimes or number of tasks processed on that CPU. So that's a further optimization that's been done. Depending on how recent your kernel is, I think that was 4 series, you might come across that problem. So aside from that, there are other work queue events. So work queues are one of the kernel threads which you can't shift off. And it's basically there as a way for the kernel to schedule arbitrary tasks on any CPU. And you can have a look at what's happening by using perf. So I mean, you can just go and leave that running on a CPU for a bit, and you'll kind of see the kind of things that the kernel is scheduling in terms of housekeeping tasks on your CPUs. And you know, if you find something that is routinely kicking off user threads, then that's a really good starting point for going and figuring out what that event is generated by and walking back up the kernel source to find out why those tasks are being executed and if there's anything you can do about them, because usually there'll be something you can tweak in order to get that to not happen. So for low latency as well, interrupts we need to care about. This is kind of a side thing, but the hardware devices plugged into our machines are signal their readiness by firing hardware interrupts to a certain interrupt line, which will be associated with a given CPU. So your network card, depending on which mode it's in, every time a packet is received, it will generate a hardware interrupt, and that will kick off any executing software task on the CPU to which it is targeted. So if given our CPUs that we want to isolate of 0 to 5, we'd want to make sure that in procIRQ for all the interrupts within that file system, we can set the CPU affinity to make sure that they're not going to fire on our low latency CPUs. And general practice is just to assign a core, if you've got enough spare, to handle all the network interrupts, and that way you kind of don't have to worry about it. Timer ticks are another mechanism that the kernel uses for timekeeping and for housekeeping. They're generally scheduled at about 1,000 per second by default on server class systems, might be a bit less on your laptop. And these are signals which are raised that frequently on every CPU in the system if you don't configure it to stop it doing that. So these again are going to kick off any software task which is executing. And we saw quite a lot of jitter over this. And there's a way to deal with that called tickless mode, which I won't go into here, but it basically means you can instruct the kernel that you want these CPUs to be not interrupted by timer ticks if there's only one task running on them. And because we've done the correct CPU isolation and used shared set affinity, we know that only our application threads are going to be executing on those. So that also gets you a really good win. It just means that once you've kind of applied all these things, your user programs do just get to execute all the time, and everything goes a lot faster. It's very gratifying. CPU governor. Our systems have to make a balance between power saving mode and full-on performance. So almost all modern CPUs will have some sort of throttling capability where they'll kick down into lower power states if there's no work being executed on them. And it's the job of the operating system to kind of manage that. So the scheduler in particular, if it detects that there's nothing to be executed on a CPU core because all the threads which are in its run queue are blocked on I/O and there's nothing else in the system which wants to run, then it can just power down the CPU, which is great for data center and electricity costs, but there is a cost to pay in terms of latency for kicking that CPU back up into fast execution mode. And that is controlled, at least on Linux systems at the moment, by having a look at that place on the file system. So there will be a couple of different options. It's fairly obvious. One of them is power save and one of them is performance. Set it to performance and surprisingly things go faster. Also, on a lot of CPUs you'll have turbo boost, which is another feature which can boost the frequency of one core for a short while, but it also means that the chip can then exceed its thermal envelope and it causes all the other cores to be throttled down to cool down. And this all happens very quickly, but we found that we got much better reliable latency by turning off turbo boost because it meant that everything kind of stayed at the same high clock speed rather than flipping up and down frequently, which is what we're seeing when we had turbo enabled. Right. Do we have many computer scientists in the room? Oh, only a few who will admit to it. Brilliant. Okay. So I was going to say let's do some science, but there aren't that many computer scientists. So I'll just talk about some numbers. Okay. I've talked a lot about the techniques, so I can kind of back it up, which is nice. I'm going to use interthread latency as a proxy for system jitter. So if we have two threads which are just trying to pass a message to each other over some fast transport, perhaps a disruptor, and we time the taken between the producer and the consumer thread, and we chart it over time, and we record that time, then we can compare how long it takes to get a message between A and B on a tuned system and a non-tuned system. So just the untuned system is, I've got a large machine, I write my Java code to ping pong some messages, start it up, record it, and chart it. And then the tuned instance is when I've applied all the kind of techniques that I've talked about so far. And onto some numbers. So this lovely chart table will tell us that a tuned system for mean latency will be a mere 216 nanos as opposed to 466 nanos. These are the kind of numbers that I get terribly excited about. It may not seem like a lot, but it is a doubling, right, which is kind of interesting. But more important is the kind of variation you get towards the long tail. So earlier on I was talking about jitter being manifestation of the long tail. So we can see that the max numbers are the same for some other reason, but as we get to the higher percentiles, the untuned system is taking a bit longer to respond. And for those who like their numbers in visual form, this is what it looks like. So green, oddly, is the untuned system. So green is bad, red is good, and lower is better. I hope that's clear to everyone, right? But we can basically see that the interthread latency is very good for most of the time, and then as we get up to the sort of 0.1%, 0.01% and higher, the tuned system looks a bit better up towards those percentiles. And I think there was something like several million samples in this chart. If we look at it on log scale, on the y-axis, we can see that at every percentile, there's quite a big difference. There's something oddly systemic going on around here. But the tune system is always better by kind of a logarithmic amount, if you will. But you can see that there's a clear win. It's a bit hard to see on the previous one because you've got the collapsed y-scale, but here you can see that it's worth doing. Now, as impressive as these numbers are, these were generated on a quiet system. So we have what was it, a 48 CPU box with 128 gigs of RAM and doing absolutely no work whatsoever, and me running my tin pot Java application on there trying to measure inter-thread latency. The mean was twice as good with all my tunings applied. But really, our production servers don't work like that. We don't have these massive wide boxes doing absolutely no work. They're servicing network interrupts, they're doing logic, they're churning through memory, they're doing garbage collection, etc., etc. Using disk, and the kernel will be coming in to do paging and things like that. So this isn't really a fair test. What we want to do is compare the tuned inter-thread latency to an untuned system. And here you can kind of see that there's a slightly more meaningful signal. So the difference here is it's exactly the same code, exactly the same system between tuned and untuned, but the workload in this case changed. So I ran the same program, but I also created a thread per logical CPU on the system that would wake up every 10 milliseconds or so and busy spin for 100 milliseconds, or thereabouts. But it basically simulated what would happen if we were contended for CPU resource within our systems. So the untuned numbers, the mean in the 50th percentile are pretty good, which you kind of expect because systems are fast and it's hard to actually utilize them fully. But at the long tail, it looks really bad. So we've got 300 microseconds at the 4 nines, enough to keep you awake at night. And the maximum, nearly a millisecond, which would bring you out in cold shakes. Whereas the tune system, awesome, flat, right down the line. We still have some problems at the max just because there's a systemic problem which we later got to the bottom of. But we can see that if we have a system which is actually busy, it is possible to make sure that we can get really low jitter on the important paths that we care about. So for us, this is the network thread, which is picking things off the network, the business logic, which is doing the matching, and then the thread, which is then publishing back out to the wire. And we can say that we're going to get really consistent low latency through that path, no matter, for most values of no matter what the system is doing, and that we can kind of deal with other events happening in the operating system or other programs running. And let's go back to a nice diagram. So remember, green is bad, red is good. This is the untuned system in green and the tuned system in red. And you can see that on a loaded system, response times after the 3 nines just kind of go out the window. So that was the kind of benefit we could see on a system which is actually stressed. To summarize, the process that we followed was pretty much this. It may work for you. Select the threads that need access to CPU. So if your application is kind of leaned towards one which you want to make sure it's on CPU all the time, find out the threads that actually need to do the work. Isolate some CPUs from the operating system. Pin your important threads to those isolated CPUs. Don't forget the interrupts, because they'll kick things off, and they kind of sneak in there. You'll never see them if you're just tracing kernel code or what have you. There'll be more things. So this is a small set of all the things we discovered that fits into 50 minutes. And I'm sure there'll be more things that we'll discover in the future. Please share if you do. And we always want to test assumptions. So despite computer science not being a science, if we apply the scientific method, it makes this sort of thing a lot easier. If we can do repeatable controlled experiments with known inputs and measurable outputs, it means that you can experiment with this kind of stuff, one thing at a time, and see how to get benefits by tuning your systems for low latency. Thank you. This GitHub repo has a walkthrough of all this, so you can fork it, download it onto your system, and it will demonstrate how to do these things. Thank you very much. Any questions, or just for the pub? Oh, hi.
What utilization do you get on those cores, the ones where only one hyperthread is running?
So the question is, what utilization do we get on cores with a single hyperthread? For our use case, we'll be busy spinning, waiting for a message to come into the queue, so it's 100%. So if you're using the disruptor for the very lowest latency, you sit there, busy spinning on the head of the queue, and as soon as something comes in, you get it.
But can you measure how much of your time how much of the CPU time is useful work versus spinning?
messages processed? No, not really. That's something you'd have to handle within your application, I think. So you can, in fact, we do measure time spent not processing messages. So that could be a useful metric. So within your event handler, when you're processing that queue, you can record the last time you processed something. Don't update that while you're spinning, and then next time you get a message, you know how long you've been effectively just burning CPU.
If you were to take that, the ratio of that to the stuff that is not isolated, when the OS is running, what would that fraction look like? The question I'm asking rather is why only 3 threads? Do you not have more work to do which needs to be loaded?
So we generally, I think on our busiest systems, we might have 7 or 8 hot threads. And we've got systems just wide enough to fit that on one CPU socket. And the OS, generally you can leave it for 8 or 8 logical CPUs, and that'll be plenty. So yeah, we make sure that all the important threads are pinned and have their own core. If we had more threads, we'd need to get more boxes that are, have an infeasible amount of CPUs. Awesome. Oh, sorry. Yep.
Would it be faster to run this with a unikernel?
Yeah. I started this kind of before that became a thing, and I gave this talk at Strange Loop last year, and the guy who was on after me said, "Unikernels, you can throw away all your tuning because." I don't know enough about it, but containerization-wise, I think as long as I don't know how the scheduling is done from a unikernel perspective. If you are running a JVM within a unikernel, there are more threads than there are CPUs. So I don't really know enough to answer your question. It's something that I was going to start taking a look at, and then
So to be honest, I think Java gets supported. Probably usually it's more functional languages. They are working on that.
yeah. I think if there's a way of declaratively saying it, then yeah, cut all of this out. And it's a really interesting use case, but I haven't seen it to this degree of maturity where you can just kind of configure it for that. I'll have a look. Yeah.
Yeah, you mentioned testing. I wonder if you, after you've done all this, do you now have a set of sort of automated tests so you can tell whether one day a kernel update or something has lost time and you've lost a bit of that?
This work was done when we rebuilt onto our new generation of Exchange, and we have a dedicated performance testing environment which is running same kernel and hardware as production, and that's continuously tested, and we are looking at all the metrics that come out of it. So we have a bunch of validation tests which also go and look on all the boxes to make sure that there's no rogue processes running on all the CPUs that we care about. But it's been a case of kind of finding the little problems that have crept up and fixing them and adding tests to make sure that they don't crop up again, rather than having some kind of one-size-fits-all. Like, those are all the things that you have to go and run. So this is quite fragile in the sense that if someone isn't aware of the work that's been done or how it all works, they can break it, but that's our fault for not testing it up front. And as we find those breakages, we go and make sure that we have testing around that.
Are you tempted to write the hot parts of the code in C rather than in Java?
We have a few very small components in C, mainly to do with packet capture. We've found that decent Java code that's sympathetic, to coin a popular phrase, to the mechanism it's running on, is fast enough for our use case. I think you can play benchmark games where you can prove that this C code is faster than that Java code. I mean, if you wanted to take advantage of an advanced CPU instruction that wasn't available as an intrinsic in the JVM, then you'd get a win there, something like that. But because our infrastructure is built on the disruptor, which is Java-based, that's kind of where we write all the business code, and we don't really have problems with garbage collection anymore. So, Java is productive. We have, and all our developers are well trained in it. So we found that to be, I guess, the most cost efficient. Yes. So I guess those kind of cache pollution effects, I think, are quite hard to measure. I'm not sure we could reliably measure them well enough to say that to even write an experiment which would prove that the C code would work. You're largely at the whim of the JIT compiler anyway with what you're kind of running in terms of instructions. So if you want that level of control, then I think if we really wanted to be able to be that detailed about it, then C would be kind of the natural choice because you'd know what you were getting. But the nice thing about the JVM is that when you upgrade, you get a whole bunch of performance improvements for free from the JIT, which you don't necessarily have to learn about, which is probably quite good for being productive as a programmer. So it would be interesting, but we haven't found the need for that.
Speaking of productivity, how many changes do you make to the system? How many people work on it?
So we have, we must commit every few minutes throughout the day. There'll be, plenty of commits. We have a team who are working in Australia and New Zealand as well, who are committing overnight. We will build and acceptance test the whole system every 25 minutes or so at the moment. And I think I saw a statistic that was generated by one of our developers that said we'd rewritten about 70% of the code base over the last 2 years or something like that. So there's a huge amount of change going in. We're still building new business features. And the kind of continuous improvement and delivery process that we have means that the performance testing is just as critical as the functional testing because of the numbers we're talking about. It's kind of hard to perturb this stuff with Java code, but we have other components in the system which we know that need to run fast. So there's a lot of change, and we need to manage the performance side of it as well as the functional side.
So this is different kinds of orders. What kind of changes?
Maybe we can talk in the pub about this. There's all sorts of changes going into the system. It's quite a large, broad system, I won't bore you with the details because some of it's really pedestrian.
Sure.
Hi.
This may be remotely relevant or maybe irrelevant. In your architecture where you have the logic thread that lays out, I work on something similar in healthcare, but in my case the problem is that logic thread always has to hit some disk I/O, and whatever optimization I have around everything, it just dies the second I have to go to the disk. So in your architecture, if you have any requirements like that, how do you isolate that out of the bit that needs to be really fast?
Stick it all in memory. So we're lucky in that our entire business logic state for all our services will easily fit within. We've got servers with 256 gigs of RAM, and we're running Zing, so our heap can be up to 2 terabytes now. We don't have any servers that can do that, but our whole architecture is built on keeping the important mutable state that you want to access frequently in memory, accessed by a single thread, so that you never get contention. And anything that's kind of slower access times, we have something else deal with that. So it's not related to
what's the preferred method of connecting to that something else?
So we just use multicast internally on the bus, and for reporting purposes, we'll have another service which will accept read requests and farm them out over TCP, which is good for bulk transport. Yeah, but a tough problem if you've got to hit I/O, then you're SSDs and memory.
It's a legal requirement. That's the problem. Then
Then I'm saying nothing.
No, that's all right. You just have to hit it, but that's
Yes.
You mentioned about CPU affinity for the hot threads, but how is hot threads determined? Is that something the schedule can figure out for you?
No, so we have to manually do that. We, if you, sort of from the Java side of things, we have a runnable implementation, which is going to kind of do the work, and we wrap that within another runnable, which, when it gets invoked the first time, calls shed set affinity. The bit of detail I didn't go into. Shed set affinity, one of the arguments you can pass to it is the PID that you want to set the affinity of, or if you set that as -1, I think, or 0, it will set the affinity of the current thread. So from the thread you care about, and you will know what that is from your application's use case, you just call shed set affinity in whichever library you choose, and that will mean that your thread will get run wherever you tell it to go.
Did you get experience? So going back to like the LS Topo kind of graph where you have
PCI locality listed there. Did you get any experience with the selection of which cores to pin your worker threads that are pulling from PCI devices? Is the rule just like on the same socket, or is there anything a bit more sophisticated?
There's no sophistication in this. It's just hitting it with a hammer until it looks like how you want. So the PCI locality is important. The cost for cross-NUMA memory accesses is low. I mean, it's in the hundreds of nanos, but we definitely found that latency was better and throughput was better when our threads which want to read from the network card are on the same NUMA node or the same socket as that PCI device. Otherwise, you've just got more cache coherency traffic, and that's going to impact your system. We also use solar flare cards in these in this generation, and because they use busy polling, and there's no kind of kernel buffers in the way and interrupt handling, you're effectively just reading a chunk of memory that the driver's mapped in. So it makes sense to be on the same socket. So yeah, do that if you can.
Okay, so all cores are created equal.
Apart from the core running CPU 0. So there's a bunch of boot processes which will end up on CPU 0, which are harder to get rid of, and the kernel will keep trying to. Well, we had some problems with that. So we ended up with all our network cards in socket 1 and all our hot threads on socket 1, and we left the the very bottom of socket 0 to the OS. So it got the first 4 cores, and then we used some other stuff for pool, and then all on socket 1 was the hot threads. Oh, hi.
Are you looking at the system tab for instrumentation?
So we have a couple of our tech ops guys like System Tap. We used it a little bit, just kind of with them. We found it to be a little bit lower, higher overhead than perf to start with. But it's really just a case of what we sort of gained our expertise in. I started using perf events and ftrace because I think that's what Brendan Gregg was blogging about at the time, and that's kind of where I started from. And next time I dig into this, I'll probably use eBPF. So I haven't had any experience with System Tap. It seems a very capable tool, but I think it wasn't just right for my use case at the time. Hello.
Is there another tool, Intel PT? It's a capacity of new processors from Intel. I don't know if you've seen it. It also allows you to trace processes without overhead or with training of overhead.
What was the name of it, sorry?
Intel PT.
PT?
Intel PT.
Okay.
PT
Intel PT. Oh, right, okay. Intel PT. Okay, I'll have a look at
And
it.
you have for Linux, the Leeway PT, which works at CPU level. It's very fast.
Okay, thanks. Time for the pub. Hooray. Right, thank you very much.